Hi again, everybody. Welcome back. This is one of our last ideas of the chapter, and that's angular momentum. Now, we've been kind of going through a lot of topics in these chapters on rotational values because we've been going through them pretty quickly because we've actually had them before. Most recently, we talked about how a net force of a system is a lot like net torque of a system, all right, and just accounting for that using radii. And we had talked about rotational energy and how kinetic energy is a lot like, linear kinetic energy is a lot like rotational kinetic energy. And now we're going to be talking about momentum and how momentum is very, very similar. Angular momentum is very, very similar to linear momentum. You remember that linear momentum, or hopefully you do, is mass times velocity, all right? It's a vector quantity. Well, it's just as true that angular momentum is a vector quantity as well, and we indicate that by an L. All right? You might say, well, why don't we use an M? Well, because we've got M's for all kinds of other things right there. So in the same way that P makes about as much sense for linear momentum, L makes just as much sense for angular momentum. That's just a symbol that we use, all right? But do note that it has a vector arrow over the top, as it is the cross product of the radius vector and the linear momentum vector. So remember, linear momentum, this is like saying radius times mass times velocity right here. All right. So how do you get a linear momentum turn it into a rotational momentum? Well, think of it like well, there's going to be a problem, maybe not in this segment, and a little bit later, where you have a, I'll change colors here, we have a merry-go-round, all right? And you've got a person running at the merry-go-round with a certain momentum. In fact, I'm going to, oops, I didn't mean to erase all that. Oh, goodness. Let me draw that again real quick, all right? Person running, here's our merry-go-round right there. Like so, and they are running at it. Let's change to blue again. Like that. Okay, there's a certain momentum right there. Now I meant to draw that so that it doesn't look tangential, and it shouldn't be tangential. All right. Well, it could be, but you probably know from experience that if you want to run towards a merry-go-round and then hop on it and get it to spin, you run tangentially to it, and so that your momentum carries you onto the merry-go-round, right, and then causes you to spin with it, and then it's great fun. But you could also be running not tangentially to it and hit the merry-go-round like so. All right, we're going to talk in just a second about how we can create an angular momentum with this, even if you're not tangential to the merry-go-round. Incidentally, the way we can calculate angular momentum is radius times mv, right? Or in the same way that mass times velocity is linear momentum, and moment of inertia, this I, is our rotational analog to mass, and our omega is our rotational analog to velocity. That's our other way of stating angular momentum. So angular momentum is either radius times linear velocity, or linear momentum, or it can be stated as I, moment of inertia, times our angular speed, omega. Okay? And you'll recall, by the way, let me write this over here. That's like saying I times, how can we write omega right there? Well, that's going to be V over, R, all right, velocity over radius. There's a couple different ways to write angular momentum in terms of whatever values you have. Okay, but let's go back and look at this little merry-go-round scenario right here, and then we'll make some sense of it. So you are running with this momentum right here, some velocity. Your mass has some velocity, and you're hitting the merry-go-round right there, all right? And so you hit it at radius R, but it's not exactly tangential. It's at some sort of other angle, maybe this kind of obtuse angle. Actually, the angle would be like, let's see, let me draw it. I'll draw it in lighter blue so it doesn't get too cluttered. like that. You'd actually be hitting it at that angle right there. Okay? So you're not actually hitting it at a 90-degree angle, but you do have to account for the angle. So we can say that the angular momentum, L, is radius times your momentum times the sine of that angle between the radius and the momentum right there. All right? Or like we said before, you could say it's radius times mass times velocity. Mass times velocity is linear momentum as well, times the sine of theta. Which, of course, as we said before, is I times omega. But you could also say, all right, well, instead of thinking this as the full radius, why don't we just call it what we call the moment arm, or you might say the working or practical radius that this momentum is being applied at right here. What if we shortened this to right there? We would call that the moment arm, or the perpendicular radius, because this momentum, which I apologize, that line isn't drawn very straight, but it's this radius that momentum is actually being applied at a right angle at right there. So there is kind of your right angle, and then it's you could say this angle right here is 90 degrees. All right, so you can either say sine of theta, so r times p sine of theta, or you could say p times r sine of theta. R sine of theta would really be this moment arm right here, and that's really what the next is showing. All right, so if you come at this momentum hits a circular rotating object at a kind of a glancing angle, you might be hitting it on the outside edge, but it's really this radius right here that is the practical moment arm. So we would call that write that in blue. That's your moment arm. That's r sine theta. So like we did before with forces and torques, you can either do torque is force times radius sine theta. That would be your force times your moment arm. Or you could do force sine theta times your radius. Either way, you have to account for that angle if it's not 90 degrees. Okay? Once you've accounted for theta, then you can multiply it like normal. But angular momentum is still radius times your linear momentum. You just need to account for whether it's 90 degrees or not. So things that have momentum in a circle obviously have angular momentum, but things that have momentum in a straight line also have angular momentum. So if this object right here, this point, has momentum, and it's moving in a straight line right there, with respect to this point, it still has angular momentum because it's moving past it. All right? So here and here and here, it has kind of a glancing, the way that it's moving, it's got a sort of a glancing angle, and here it does as well, but here it's a right angle. So how it moves, as it moves past this point, only right here does it actually have a right angle radius with that point right there. So we can say that all along here it has the momentum of this p times this radius, even though it's moving in a straight line. All right? Well, of course, an object going in a circle has angular momentum. If it has, you might say, an instantaneous tangential velocity, and it has mass, and it has a radius, if it's going in a circle, it has angular momentum. But anything that has straight line velocity and is moving past an object, this actually has angular momentum as it goes around. And you can find that angular momentum by finding the right angle radius, also called the moment arm, and then the momentum p. That's mass times velocity right there. The angular momentum would be the moment arm times p. All right? Kind of a good way to sort of understand this is to look at our next example. That's example 11. Does this say 1112 as well? It does. There's two of them. Sorry. Last example we did, I think, was 1112. This one is misnumbered apparently as well. But the question is, and this is more conceptual right here, does an object moving in a straight line have a non-zero angular momentum always, sometimes, or never? Well, that's a little confusing. Does it have a non-zero never? What does that mean? Well, an angular momentum is, a non-zero angular momentum is anything other than zero. Anything has an absolute value, okay? Always, sometimes, or never. Well, we said that things that move in a straight line have, generally have an angular momentum because we can figure out that momentum, and then if it is some distance from a rotational point, we could say, all right, well, it would have, at this point right here, it would have that momentum P at this right angle radius, also called the moment arm, and therefore it would have some element of, even hypothetical, angular momentum. But what if it's moving in a straight line directly over a point? What if you were to run directly at a merry-go-round and run directly towards the central pivot point? Would that cause the merry-go-round to spin? No, it would not, right? Why is that? And by the way, it would hurt quite a bit because you'd be just running into a merry-go-round. It would not spin at all because there's no moment arm right here. There's no radius. The path of your linear momentum is going directly through that point of rotation, and so there's no radius, there's no moment arm, therefore there is no angular momentum. You can still have linear momentum until you run right into the merry-go-round, but there's no angular momentum because there's no moment arm. Here there is, because you're kind of going, if we kind of superimpose a merry-go-round right here, oops, merry-go-round right there, terrible circle. You could run kind of at an off-axis direction, jump on the merry-go-round, and then kind of spin around like that, and it would be great. But not if you're going right towards that pivot point. So if your momentum carries you right over the pivot point, the answer is no. Any other path, whether it's the one that's shown right there, or whether it's this path, or that path, or this path, or otherwise, has some sort of moment arm here, here, or here from the radius, and therefore you're going to have some sort of linear momentum, but not right here. So this is yes, and down here is no. So what's the answer? Well, it's sometimes, right? Not always, and it's not never, but it's sometimes, as long as your momentum is not carrying you right into the pivot point, which would likely be quite painful. All right? So we're going to be calling it quits for this section right here. That's linear momentum, the relationship between linear momentum and angular momentum. L being either I times our, I'll just write it here again, our linear momentum equals I times our angular speed. Also being our radius times, oops, I'm trying to write two times signs right here, times our linear momentum. All right, we're going to be going forward and doing some examples, but in future video segments. So thanks for following along, and I'll see you on the next one.